as well?
Yes, yes.
Yeah.
I think everyone can hear us. This I don't think it's working at this very moment.
Okay.
I'll try to repair this in a second. I think the battery is dead.
All right. So in worst case, I will just use arrows.
Yeah.
Okay.
Let's see if this works. But
Good morning. So it's always a pleasure to be here. Thank you for invitation. Okay, so I decided to make this talk kind of like survey talk. So I will simply present some topics related to shadowing property, which I was interested. And I worked with some people, and it's very personal selection. So it won't be like complete overview, but there will be rather some topics that over the years I get involved in. All right, so just for setting, so I will be on compact metric space in most cases, and sometimes it will be interval, sometimes maybe manifold, but a general setting here is compact metric space. So the main look or main aim will be analyzing situation for topological dynamical systems, and there will be some jumps to measure theory, but it will be from point of view of topology. All right, and here you have recall of main topological properties that you consider when you are interested in kind of global dynamics. So of course you start with transitivity, and then you probably get here to mixing, or maybe exactness, which is like step further. But there are also some properties in between. But the idea, like if you want to prove some strong results, you probably will assume some strong type of mixing, and there will be one of those in a moment. But what I will be talking about will be rather inspiration for these strong mixing properties, but looking in some kind of local behavior.
Is your key invertible?
No, it's not. So this exactness, you can have it only in non-invertible case, right? So this is step further in that case. All right, so I won't be talking much about mixing, but it will appear in some places. The main actor will be stronger property. All right. Yeah, and that's also classic. So because we are in topological dynamical system, we have always an invariant probability measure. The space of these measures is compact, metrizable, so we can also look at it and check what lives in that space. Okay, so that will be, so some of paths of research was trying to say something about this space of invariant Baire probability measures. And I will spend some time looking at that space. So one of the goals was trying to understand what's living there, okay, in that space. Sometimes it can be small, sometimes it can be large. Right. So the aim is to say something about it. All right. So of course there were tools which help in that, and one of classics is specification property. So this is something stronger than mixing, of course, and probably most of you have seen already this definition or know it, but anyway, so the idea, except the definition is quite technical, so the main idea is very simple. Simply what you want to be able to do, you fix epsilon, which is some kind of accuracy of tracing, and then you fix some sequence of time. So these are these AIDIs, where you want to make tracing, and you have some n depending on epsilon, which gives you time to switch. And then if you have this property, what you can do is that you take any number of points, and there is another one, such that you follow each of them on your intervals of time, which are here, but then you leave time for switching. So like if I'm going to draw it,
The right direction.
so it would be like, okay, I have these points, I fix some segments of orbits. And then if I have specification, with some accuracy, I can follow that orbit to go somewhere else, but I have time for switching. This is this n.
The time of switching is at most n, not at least.
At least. So I need
So
n or more. But
you allow very long time of switching?
yes, but I don't want to do that, of course. But I'm allowed.
No, but if you,
I can do it, but the question is why, right?
No, but here it is written like that.
Yeah.
for
Minus n.
n, for n, so
Yeah.
there's a
So
lot
the
of
gap must be
numbers.
at least n, but it can be
For
longer,
n, okay.
right? So maybe I'm interested to make it n plus 3 by some reason.
For n, then.
Yeah. Right, so I'm switching, then following, we go somewhere, but I'm switching here, and sometimes maybe I can even loop it into periodic orbit, and I have periodic specification property. Right, so what I have here, I can control where I am by taking these places in space, and there are some parts of my tracing orbit where I'm not controlling. I can be anywhere, and of course when epsilon is small, n is probably very large. Okay, so if I want to increase tracing, I need more time, and then my point goes somewhere, and I'm out of control what's going on, and that's some trouble which you will see later, why sometimes it's not good. But on the other hand, I can make that segments as long as I wish. So the idea is like looking for point of view of averages, for example. I can make, so this n is a priori given for epsilon, but then I can make these orbits very long, and then I don't care, for statistical point of view, I don't care about this switching, if these segments are very, very long. Okay, so that would give
Can
me...
it be better? I mean, obviously you need to have some time to switch, right?
Yes, but you will see.
There is
Okay.
better.
There is better in a sense, worse and better.
Okay.
You never have two things for free. Okay, so why people were interested? So here you have these classical results again. So for that talk, that one is the most interesting, probably. That was the start. So there is result of Sigmund, who proved that if I have specification, I can take any invariant measure and I can approximate it by ergodic measure. Only in case of periodic specification, this ergodic is even sitting on periodic point. Okay, so that's very nice. I mean, you more or less control the space of invariant measures. You take any measure, it's probably not ergodic, or maybe you can take two and average them somehow with some constants, and then there is one very as close as you wish, which behaves like this one.
Must follow from Virchow.
So the idea of the proof relies exactly on that. Like you take generic points.
You need to have long block of
Yes.
detectors. That's why
Yes.
Virchow.
Right, so that's trick of Sigmund. At least it's what I learned from him, and then if people try to make something like that, it's very much relying on that approach. Like long segments of generic points and then switching and calculating. Okay, so that's the idea. Okay, and here is one remark that there are also some cases when you have this specification. So, for example, on interval, every mixing map has periodic specification. That's also odd result of block. And there are other examples. So that property is maybe not that common, but you can find it.
Finite graph or
Topological. So, yes, fine. Topological graphs.
no? We have infinite.
Yeah, so finite
Edges.
number.
Finite number.
And the first result was for interval.
It looks like generalization of
Right, and nice proof of this is by Bouzy, more recent one. All right, so that's about specification. But then you can ask more. Okay, so let me go back. So here in Sigmund, I can approximate any measure by ergodic one, but if I'm on periodic orbit, which is probably the case, the entropy is different. Right? Here I have zero entropy, and there were related questions afterwards, which are also known. Right, and there is also like part of questions, so people are also interested in measures of maximal entropy. So this approximation, which we will see later, this type of approximation related to entropy. So people are asking about measure of maximal entropy, where it's finite, it's ergodic, and then there are questions, okay, when I can find it or where I cannot. And in case of specification plus expansivity, you have this measure. All right, but that will follow. All right. So of course, not always you have measure of maximal entropy, sometimes you don't. And here is kind of surprising result, at least for me, of Rouet. So when you are even on interval, if your map is nice in the sense that you have finite number of monotonicity pieces, or if you are very smooth, then you have measure of maximal entropy, but if you drop this one to CR, and you are mixing, which means you have specification, then it may happen you don't have this measure of maximal entropy. So this is paper by Rouet, and this is quite involved construction. So there is no, what I'm saying, there is no connection between specification and measure of maximal entropy. So although this specification is very strong property, and it even helps you make this approximation, it doesn't give you everything. Okay, and what I was saying, there were questions related to what Sigmund proved. So I showed you, he proved you can approximate measures by ergodic measures. So then people ask, okay, what about entropy? Okay, and here you have one approach, which is from paper of that three guys, Eisenberg, Kiefer, and Weiss. So the property is, okay, you give me your measure, you give me some number below entropy of that measure, and I can find ergodic measure with entropy above this number. Okay, that's entropy approachability. And here I can be overshooting very much. Okay, but I don't care. I want to go just over that number, but maybe this number is not close to this one. It may happen. Okay, so I just want to measure some entropy very as close as I wish, another one ergodic with sufficiently large entropy.
The first one should be true for any dimension which looks like Yongi. C infinity implies asymptotic H expansiveness.
Okay.
I think Yongi. I'm not sure whether it is for non-invertible or completely general. Diffeomorphisms. C infinity, I think it's Yongi. It's much more advanced.
Okay. Right, so coming back, so what they prove, specification gives you this one. And that's also, in some sense, surprising that although you can make this, you may not have measure of maximal entropy. Okay? So I get this measure, but it's below this supremum, and then I can go above any number with ergodic, but still not reaching measure of maximal entropy. All right, and usually to get measure of maximal entropy, you need some.
In the classical variational principle, you can always take supremum over ergodic.
Yeah. So supremum you have, but you don't have candidate which
I know, but
right?
I just say I don't find it surprising.
That you don't reach it, even if you can go.
It's the same situation with Gemini.
Yeah, maybe you are right. Right. Okay. Yeah, anyway, I would expect that if I can approximate, and maybe somehow I can produce something above, but it cannot happen. Okay, so now I will, so that was like introduction, why some questions will appear. And now I will speak about shadowing property, which in some sense is stronger than specification. So some results will be repeated, but then I need something extra compared to specification. Okay, so what's the property? in some flavor is similar to specification. In fact, it was probably motivation for specification property, that one. So what's the difference? So I don't have segments of orbits. Instead, I have pseudo orbits. Okay, so I have this sequence. So I can, in each element on the sequence, the next one is close to value on previous, right? So it's, okay, let's do it just to see the difference. Okay, so I'm like this. Right, so maybe even more. Here I had segments of orbits, here I have not exact orbits. I have this epsilon for delta, so this mistake here is delta, and then I can trace with epsilon, so very similar to specification. Right, I was also able to trace with epsilon. I don't have this n, so I can trace everywhere. Okay, so every element of the sequence I'm close by epsilon, so I don't have these gaps, let's say. But what I don't have, I cannot go everywhere. Okay? Here I could choose anywhere in the space and I could just jump. Here I don't have this freedom because I have to be able to connect by this sequence. And maybe it's impossible sometimes. Alright, so that's what I'm losing. I'm getting rid of that, which is possibly a bad thing. But what I'm losing is like global dynamics. Right, and in classical, it was usually connected with expansivity, and the reason for that, inspiration was by hyperbolic dynamics. Then people start to just use this definition, forgetting about like derivatives and other things. But still, the reason for that was this theorem, why people like shadowing expansivity. So
the reason was structural stability.
Yeah, also.
You can approximate
Right.
delta after perturbation, trajectory becomes delta trajectory.
And then you can do
in hyperbolicity, you can approximate by trajectory, and you can consider also dynamics on more than one trajectory, and this gives proof of structural stability.
Yeah, but the advantage is structural stability, right? Here you maybe don't have it.
Yeah, but this theory was also
right. So that was started.
And Bowen in the West.
Right. So okay. So these are like two nice properties you get. So if you combine shadowing with expansivity, you get these two nice things. So first of all, a non-wandering set decomposes into finite number of pieces with transitivity on each, and then on each transitive piece, you have further decomposition into mixing for some power. Okay, so that is very, very special case. I will show you later. But the problem is that by many reasons you usually cannot have this property. Okay, so in a moment I will show you why you usually don't have it. One of the reasons is that on some spaces you simply cannot have this property. Like on interval it never happens to have expansivity. But there are also other reasons. But usually shadowing is quite common. Okay? So that property is much easier to observe. That is kind of unique one, very special. So also this decomposition is very special, but if you have it, it's very nice. Right, so you have, it's not written here, but in fact on that pieces you have specification property. So specification naturally arises under this. All right. Okay, so what I was saying, that expansive situation is very special, and this is kind of surprising thing. At least I was surprised when I saw it first. Okay, so the result is that if you are on Cantor set, and if you are equicontinuous, you have shadowing. And equicontinuous means for every delta there is epsilon, such that if you start at delta, you stay epsilon close forever. Okay, so I will write it. Okay. delta such that if 2 points are close, then where we are. Okay, and on Cantor set it means implies shadowing, and then you take identity, and by some surprise identity has shadowing. And that's okay, not what you would expect. Right, but that's a very easy example. And then for sure you don't have this decomposition I was showing you. Okay, I didn't say what are chain recurrent classes, probably I should say that. Okay, so let me go back. Okay, so here I have definition of pseudo-orbit, and then I can check, I can take 2 points and I can check if I can go from with delta pseudo-orbit for one to the other, and maybe I can come back. And chain recurrent means that for every delta I have this delta pseudo-orbit coming from starting at my point and coming back. So this chain recurrence, and that's the equivalence relation, this chain relation. So we can speak about chain recurrent classes, meaning some equivalence classes for this chain relation. Alright, so in that case, these were chain recurrent classes for this decomposition, but in general you don't have finite. You can, like with identity and Cantor set, every point is chain recurrent class. And that's the reason why you have shadowing, because you simply, if I decrease delta, I cannot jump very far on Cantor set. So no chance for these spectral decompositions, but you can still have something which is similar to some extent. So under chain transitivity, you may think just under transitivity. Chain transitivity means you can go anywhere by delta pseudo-orbits for any delta. So if you have this chain transitivity, or for simplicity, if you have transitivity, then you have two situations. Either you have chain mixing, which is like in definition of mixing but with chains, so it means for some large n I can go between any 2 points with delta pseudo-orbit of that length. So either I have classes when I have chain mixing for this iterate, so okay, going back, so either I'm like here, okay, because I had this sets in decomposition when I had transitivity, and then there was decomposition into permuted sets when I have had mixing. So here the same, I see something like that, I have chain transitivity, it decomposes into some number of pieces and they are permuted, and on them I have this chain mixing. Or, that's another case, I have odometer as a factor. Okay, so there is no finite decomposition, there is this odometer, so there are lots of classes and they go in cycles and cycles and cycles. Okay, so in some sense it is similar but a little bit more complicated. And also odometers are not by accident there, because what is known is that odometers are the only minimal systems with shadowing property. So if you want to have shadowing and minimal, it must be odometer. And if it's not minimal, you have positive entropy under transitivity. Right, so if I'm transitive but not minimal, so entropy rise. Okay, and also if I have shadowing, then if I have total transitivity, immediately I have specification, or with expansivity even periodic specification. So in this case of transitivity, shadowing almost implies specification. So in that sense, I would, if I assume shadowing and maybe say I have transitivity, I probably want to get more than I was able with specification. That would be natural to expect that, because otherwise I simply could use specification and have the same. All right, so that's one of projects I was involved with Jian Li. I will present it in simplified version, just to not make it overcomplicated. All right, so this is some small summary what was known about specification. So for every invariant measure, first of all, I was able to approximate by ergodic measures. So that was Sigmund result, and this vice result was saying, okay, I can also make this convergence with entropy going above my entropy. And okay, if entropy function was nice, then usually you could show that you have measure of maximal entropy, or make this maybe exact limit. Okay. So with Jan, we were inspired with that, and we were checking what we can show. So now we have just shadowing. Here I'm putting transitivity, but we have the result without transitivity. It's simply more complicated. So I have to say more if I don't have transitivity, and it's local on time recurrent class. But for transitivity, what you have, so first of all, you can approximate like here, although you don't have expansive, so it may happen that you don't have periodic orbits like in Sigmund, but you have odometers. Okay, so that's the price. And what you can also do, so here under shadowing you not only have this thing, but you can get exact convergence. Okay, so you give me your invariant measure, and I give you a sequence of ergodic measures that entropies converge. Right? So I'm not overshooting in that sense, and I also know what's the underlying support of that measure. So these are just toplet systems in a sense. Okay, and what we don't know, so this proof we have, it doesn't work for specification, and the main reason is this part. Okay, so we would like to spend some time trying to prove it under specification, but we don't even know if it's true. I mean, about that case. Okay, if I can really have convergence, or if I can say anything about these supports, because I have this. If I want to approximate my measure, I have to go very close to some generic points, but then this gap grows, and maybe I'm everywhere in the space, so I don't have control. So for sure that result, this proof we have here does not work, but maybe something like that is possible. We would really love to have something like this, but we don't know how to do it.
Invent some different properties, slightly stronger.
I don't know. I would like have
Because
different
you don't know
classes.
what's the relation of capital N to epsilon.
Yes.
If you assume something.
But still it's fixed, so that's very, very long. So maybe for ergodicity, I don't care about it, but if I want to say what support, I care very much. Right? Because if this is long, maybe I'm visiting the whole space. But on the other hand, in Sigmund, here you have periodic orbits, but that is because of expansivity. Okay, so I don't have expansivity. All right. And what we also observe, so we for sure know that that's not enough for shadowing is not enough for having measure of maximal entropy, unfortunately, and we believe that something like Rouet bit is possible, so maybe on interval it also holds, but it seems very complicated to provide examples. So we were not that motivated to repeat what Sylvia was doing.
Sorry to interrupt, there's a question from the online
okay.
audience. Does specification and transitivity, does it imply chain transitivity? I'm just reading the question. Specification plus transitivity, does it apply chain transitivity?
Okay, so I should say maybe this. Okay. So chain transitivity means that for every point in my space and for every epsilon, or maybe delta, there is delta pseudo orbit from x to y. Okay, so I can move from x to y with delta pseudo orbit, and if I have transitivity, I can even do it with exact orbit except the last step. And because if I have transitivity, x and y, these are some open sets. So here I can like start with some point and go there. So transitivity is stronger property, is what I'm saying. Chain transitivity is something weaker, but you usually use it because if you have shadowing, then chain transitivity plus shadowing implies transitivity. So that's why this property came into life. Right, so answering the question, transitivity is simply stronger. Right, so I was talking about Sylvia's results. So that what we have here is like first step. So she was first doing some abstract construction on some infinite combinatorial graphs, and then by some very, very careful technique was plugging it into intervals. So we like make something similar in flavor to her first step, but never did that one. So we hope it can be done, but we never tried. All right. So now a little bit about shadowing and why or where you can find it. So that was mentioned, hyperbolic dynamics, that's maybe the classic one. But then the properties start to live its own life in the literature. So what you have generic case, so now on many manifolds, for example, you have it in many spaces, you can prove that typical maps have it. In C0 topology, I should say. So if I take C0 topology on manifolds, for example, or on surfaces, then this will be typical property, and expansivity usually is not. So it's why you don't combine two, because you want to work with this generic property and try to say something. What's typical, what happens in typical maps. So it's why only shadowing without extra things. So you usually don't have transitivity, you don't have expansivity, so you have to work locally.
Generic in C0.
In C0, yes, in C0. And that's also a nice example. So on the interval there is a paper, I believe it's Cohen, Kahn and York. Definitely York is one of the authors that I for sure remember. So they consider 10th family. Right, so 10th family on the interval. So we have full 10th map, and then you start to decrease the slope. So you are, in the paper, you are between square root of 2 and 2. And what they prove, I now don't remember if it's for 10th map or core of 10th map, so that I don't remember, but I believe it's for 10th map. So what they prove that if you start doing this, so changing the slope, so maps are very similar, but slope is changing, then you will have for dense set of parameters, you will have shadowing, and for complement, which is also dense, you won't have it. Okay, so although the maps look very similar, they are, something changes and they are behaving differently. In a moment there will be conditioning, which in fact is responsible for that. Yeah, and that was I was saying, expansivity, you never have it on interval. So expansivity is impossible property on interval. Right. Okay, so that's again kind of like technical property, but it can be explained quite easily. Okay, so this property of linking, think about it for piecewise monotone maps, for example for 10th map. So what you do, you first of all take set of all critical points plus endpoints. Okay, so like for full 10th map I take these 3 points. And then linking tells me, so I have linking on my set, means, okay, if I take any point from my set, so here is A, okay, if I take any point from that set, I can find another one such that if I start close to my, if I start close to my desired starting point, I will follow its orbit by epsilon, it's here, and at the end I will hit another one. Okay, so simply it's like that. I have these 2 points, x and y, and the x is going somehow, and then there is another one which will stay close, and then at the end it becomes y. Okay, that's linking. So if you look for full tent map, you have these 3 points, and you have linking because you exactly take any one of them, you will finish here. So you can even use your point from your set. Okay, but sometimes it's not that nice. And that's, I remember well, Cohen, Kahn, and York. So the first, there was this result for tent maps, and then Chen made, who was, I believe, student of York. So in his stages, he get this result. He said, okay, if I have map with constant slope, which is expanding, so greater than 1, then linking is the same as shadowing. Okay, and that's like generalization what was for this tent family. So here you have exactly, if you know this result for tent map, you get it has shadowing, right? Because I have linking, so it has shadowing. And that's how it was proven for this tent family, more or less. So for some slopes, you have this linking, for some others, you go somewhere. You can imagine that, like, for example, if this top vertex will be attracted by some periodic orbit inside, and you won't have linking because you will be trapped and never can go anywhere else. Right? Because I have to stay all the time epsilon close, so with small epsilon I will finish close to that periodic orbit and won't get out. Alright. And that's example we have with Chriswood and Mate pulleys. So we were thinking, because it would be nice to have like characterization for like interval maps saying, okay, this type of behavior characterize shadowing. We were thinking about it, and here you have example that this constant slope is not enough. Okay, so we can do that. Right, so what he had, constant slope but finite number of pieces. That was linking, means shadowing. Okay, and then we make this example, so you can exactly calculate what should be the slopes. So map looks like that, you have these boxes, and on each box you have this type of zigzag, and you repeat it. So slope is constant, but it's taken in a way that these points are looping. These critical points are looping. Right, so you have this linking, because for every point you are linked to some other, so that's okay. In fact, you are linked to it yourself. And with that map, we don't know if it has shadowing or not, but what we did is we took like doubling of that one. So what we did, we just took that graph and we put it here, so it's like, so it goes in loops twice. So like graph of this one, but rotated. And then at the end, we get map like this one, but it cannot have shadowing because this map is not mixing, but it should be if it was to have shadowing. Okay, so the message is okay. We don't have good generalization of this linking. We don't know what to do. So even on interval, it's not clear how to characterize shadowing exactly. What are the properties? But in nice cases, this result is telling you. how to construct map with shadowing. So like if you, for example, want to construct Markov map, then you have your procedure, what you should do. All right. And when we had this this result with Jan, so what we proved was that, okay, there was plenty of odometers. It left me a little bit unhappy because I was expecting that, okay, if I have this shadowing, there will be different minimal sets. So I was thinking, okay, what you can do to have something more interesting than odometers? I mean, is there any, like, add something, put some extra assumption, and then will you have something more interesting than odometers? And okay, here is a small comment that sometimes it's impossible because shadowing survives taking products. So if I take your favorite map with shadowing, take it in product with odometer, then I will have odometer on one coordinate, and then all minimal systems will factors into odometers. So that's bad case. But I was thinking, okay, maybe something. If I take odometer on one coordinate, I'm not mixing, so maybe mixing is solution, or I don't know. So that was a question. I still don't know what to say, but at least I can show you in a moment some partial answers. Okay, and maybe that's also worth to mention. This result also quite odd one. So it's again about interval and shadowing. It came from paper of Kuchta. So he says, okay, I have function on the interval, and I say it's string function. If I have periodic intervals, nested sequence of periodic intervals with increasing periods, then diameter should go to 0. For him, it's a shrinking function, and here you have kind of this, right? So here I have this interval, it's periodic, but here I have another one. It has period 4 and another one period 8 and so on. In fact, this map here is kind of classical example of map with odometer on interval. So this map here, it has odometer and it has lots of periodic points. So here is fixed point, here will be point of period, no, here, point of period 2 and so on and so on. At the end, if you intersect all that intervals, you will get odometer. So this is Delahaye example. It appears in his paper, and one of classical examples of map with odometer. Okay, so it satisfies this definition, and what Kuchta proved, he said, okay, if I have 0 entropy, then shadowing is exactly a function. Okay, so if I'm in 0 entropy case on interval, what I can see, as minimal subsystems, I can see periodic orbits or odometers. And he says, okay, if you see odometer, then it must be like, very roughly speaking, odometer without blown up points. It must be just regular odometer. And that's this condition. Okay, so I don't have in periodic sequence, I don't have in the intersection non-degenerate interval. So at the end I have odometer. Okay, so that's like full characterization. What can happen in 0 entropy. So at least in 0 entropy case, you can say when you have shadowing, except it's not interesting case, very much not interesting. Okay, but I'm showing this example also by some reason. Okay, so it's visible on that example. Okay, so here, as I said, I have this period 2 interval, then 4 intervals in period, then 8 and so on, and here will be some odometer living there. Okay, there will be odometer. But I have also these periodic points. So I have fixed point, point of period 2, point of period 4, and they approximate this odometer. So each of these periodic points is one chain recurrent class, but odometer is another one. So in this theorem I was showing you of Sigmund or others, it was telling, okay, if you give me your invariant measure, I can find sequence converging to it. Okay, and here what may happen is I will have this odometer, I will have ergodic measure on it, but my approximating sequence will be coming in some sense outside from the class. It's not in this class. It can be these periodic points approximating the measure, approximating and accumulating on it. So that's also something that probably you cannot get rid of. So in that all that proofs on that result, you take your invariant measure, you start approximating it, it lives on some chain recurrent class, but then approximation is living outside, and that makes some troubles. And at least we don't know technique how to make this construction inside of the class. So all techniques I know, they use approximation, so these measures or these approximating points maybe go outside of the class. Why it's bad, you will also see, or why it make troubles. Okay, maybe I will skip that. I will maybe come back to this later if I have time. Okay, I want to speak a little bit on this. So for that slide, I maybe will have time to come back. All right. So another related topic to measures and to these approximations is irregularity. Okay, so if you work with ergodic measures, you like these averages, and you know that almost everywhere they exist, whatever function I will take. And then people start to ask, okay, so what about irregular points? So what about points where this limit of Birkhoff average does not exist? So from measure theory point of view, it's not interesting set because it's a set of measure 0, but maybe from topological point of view, it's interesting. And that's kind of like difference between, again, topology and measure theory, you will see. Okay, so this irregular set, so first of all, you just take functions, continuous functions, and you check when you don't have this limit, and then take union over all functions. So this is irregular set, and that one is phi irregular set. So I can have it for one function, or I can have it like globally for the system. But and as I said, measure don't see it. Invariant measure do not see it. Right. Okay. That I will maybe skip. So here entropy which will appear it will be on a non-compact set. So on previous slide I just had some recall how you can calculate. Alright, so again it comes to specification property. So now I have this set of irregular points, which is some non-compact, non-invariant set in the space. But I still can calculate its entropy. So it's not subsystem, it's just some subset. But I can calculate its entropy, and okay, what was observed, as you see, it was like evolving. So it carries entropy.
Why do you say it is not invariant?
Is it or it's not? Let me think.
It
is invariant.
It
is invariant. It's not, but it's not closed.
No.
It's not closed. Right, so it's not subsystem. Right. Right, okay. Right, so even here it cannot be closed, right, by this result actually. Right, so what these people proved is that, okay, if I look at that set, either I don't have irregular points or I have lots of them. So from topological point of view, all interesting points are irregular. From ergodic theory point of view, all interesting points are regular. Okay, so this is kind of dichotomy. Right, and because it's dense, it cannot be closed. That's one of the reasons. All right, and right, and under specification, you have similar result for this localized localized irregular sets. And then we were thinking about shadowing. So this was first paper. It was with Sweet and Tian from Shanghai and his student Yue Dong. Alright, so what we proved, it was for shadowing, okay, so no more global dynamics. And first result was for this irregular set. So there was two cases. If it was empty, entropy was 0, and if it was non-zero, then it was carrying the full entropy. Okay, so there were like two possibilities. Although we don't have transitivity, so that set is probably spread somewhere over the space, and it's hard to say which part of space is responsible for that. And later we were doing this for these local functions, and for them you won't have something exactly like that, but something very similar. All right. Right, so this is like local version of that. So I was saving you this type of statement for this approximation result. Okay, so because I'm working with shadowing, I don't have transitivity, so I have to look at chain recurrent classes. Let me recall, chain recurrent class is like set such that between any 2 points I can move with delta chain for any delta. Okay, so I look at these classes, and now what I'm saying that if I have function such that this set of irregular points is touching my class, then entropy of this set is at least the entropy of the class. Okay, so if I touch it, I know the whole set has at least this entropy that the class had. And of course, if I was in case of transitivity, I will have equality here, and that would be entropy of the whole space. Okay, but I don't have transitivity, so I can have only this lower bound. Right, and then we were thinking, all right, so it would be really nice to have equality here. So how to do that? But we couldn't prove it. Here, I would like to have, okay, or somehow I would be happy to like connect, maybe take all classes that intersect this and maybe takes like in variational principles supremum over these classes and have equality. That I would like to have, but that we were not able to prove. We have weaker condition. We see it here. Okay, so if I look at entropy of that set, then I take supremum over entropy of classes, chain recurrent classes, but here I want more. Okay, so here it was enough to intersect the class. Here I'm saying I'm intersecting different set. I will explain it in a moment. Okay, this is bigger set. Okay, so what we would like to have is like cross out this omega here and have this condition. I intersect the class, I take entropies of that classes, take supremum, and I get entropy of the irregular set.
What is y on?
Yes, so it's
what is the
okay, so
here.
Right, so this is set. It's maybe much bigger set because I'm putting here the whole basin of attraction of the class. Okay, and it can be really large one. And we don't know how to cross it out. So what in particular can happen that maybe on the class this function behaves very well. Maybe I have this average is well defined. But maybe the reason that I don't have convergence lives outside on points that converge there. So maybe very close to the set, something happens, points like approach it differently, and then it destroys this Birkhoff averages, but on the class maybe they behave well. And we were really struggling to like cross out this omega, but we don't know how to do that. So that leaves us with a little bit unhappy, but well, we don't know we tried hard, but we don't know how to do that. Maybe some other approach is needed to do it. But we would be very happy to have this y here only. Right, and that's very short comment related to that one. So also, like, quite recently, people start to think about mean topological dimension or mean metric dimension. And the reason for that is that, okay, if I have infinite entropy and I want to distinguish between sets, then I'm adding this one, this number here. Okay, so when calculating entropy, I would just have this number, but now I'm dividing, so here I have the same epsilons, and I'm hoping this will be some, maybe not infinity, maybe it will drop down. Right, so just to show it, so that's very similar. Is when we learn that, so when we learn how to get this result, and that one was technical but not like big deal. The essence was there. Okay, so simply what you get also estimates from below. So before we had these estimates with entropy from below. Now we have also for this dimension. But here you have epsilon. Okay, so this is related to this omega which was before. I simply, for the proof, it's not enough for us to look at the class. We take very tiny neighborhood, but still some neighborhood, and calculate there, and then it's necessary to get these estimates. And the reason for this trouble and the previous one is that what I was trying to show you, that when I'm approximating measures, then what may happen, I'm approximating, but I'm going from outside of the class. Okay, so that gives me, in some sense, control where I am. So I'm approximating, but maybe from outside of the class. But then, if I'm very close, I will be very close to the class, and that's the reason why these things appear there. Right. And yeah, again, we would like to get rid of this one, but we don't know how to do that. So somehow, maybe some fresh look is needed. All right. Okay. This is also about typical shadowing, but a little bit different space. So at some moment, I get involved in work with Joseph Bobok, Serge Trubetskoy, and Pierre Meychinge, and we were trying to understand the space of interval maps preserving Lebesgue measure. So very special class, but still it's nice space because it's closed set of space of all interval maps. So you can speak again about these typical properties and things like that. And it was very much inspired by previous works by Serge and Joseph. Right, so they had before papers saying what's that typical properties for that maps, and what was nice and what is much nicer compared to general interval maps is that in case of maps preserving Lebesgue measure, you have this is with mixing with respect to the measure first of all, so you have strong ergodic properties. You have this exactness I was showing you, or mixing, if you remember the definition. You have specification, so lots of nice properties or strong properties in that maps. When I'm in general interval maps, I don't have even transitivity. So if I put this extra assumption of having invariant Lebesgue measure, then I get very nice maps. But still space is very large one. Okay, and we were working on those. this was not our main goal, but somehow we get it as byproduct when working on those maps. Okay, and this is one property I want to mention. So this is kind of, this S-limit shadowing is kind of extension of definition of shadowing, so making it stronger. So again, it can be just the definition, and I will try to give you explanation what this property means. So this is really strong one. So this S-limit shadowing. Okay, so in case of shadowing, it was like that. I had this, for epsilon I had delta, such that if I had delta pseudo-orbit, then there was a point tracing it in epsilon. And this S-limit shadowing additionally says that now if, so here was delta, but if in this pseudo-orbit these errors go to 0, then my tracing also, the error of tracing also goes to 0. Okay, that's the property. Okay, so it says, okay, if I have pseudo-orbit, I can trace it, but if additionally is asymptotic pseudo-orbit, meaning the errors, so asymptotic pseudo-orbit means if it goes to 0, then also tracing is asymptotic. Right, so this is much stronger property. And this property alone sometimes is called limit shadowing without talking about delta pseudo-orbit. So limit shadowing is if I have sequence where these numbers go to 0, limit shadowing means I have point which asymptotically trace this sequence. So this is a combination of shadowing and limit shadowing. And limit shadowing alone is much weaker. Alright, so why I'm talking about this property? Because it was known for like many cases that shadowing is generic. Okay, so like as I said, on manifolds on different spaces, it was known, okay, shadowing is typical property, and then this S-limit shadowing appeared. And often it was possible to prove that it's dense. Okay, so here I'm showing you result for this lambda of I, but on manifolds, usually when you, maybe not usually, but in many cases, when you like look into the proof that shadowing is generic, maybe you can somehow modify it, modify the technique, such that you prove that this property is dense. Okay, and you have only density, not generic property, because usually in the proof you have to make very specific perturbation and then perturb your perturbation and so on. For having density delta, you must work on open sets, but for this property, if you like look into the proof and try to prove this as limit, you have to make particular sequence converging to something. Okay, in a sense. So this property is not behaving well with, like, let's say, uncontrolled perturbations. All right, but still, we were hoping that maybe this property is generic, and we're trying to prove it. And where we succeeded, so we succeeded for a circle, and in this Lebesgue measure preserving case. Okay, so it seems to first example, at least the first case, I know that it was possible to prove that this typical property. And on interval only density, and very roughly speaking, it was possible here because there is no endpoints on circle. That's very rough explanation, but yeah, so it's like shadowing, but if I have my pseudo orbit which is asymptotic, so meaning the distance, then I have tracing. Okay, so with that one we were able to prove it's generic on the circle. So we were hoping that maybe you can generalize it. So hope is here. Okay, so this is also not so odd result. Grant 1 UNF. So if you look at again zero topology, so if you look at homeomorphism, volume preserving, then shadowing is generic, so it's like something like here. Okay, no, sorry, something like I don't have it. I have it here. Yes. So for interval, this periodic shadowing was generic, and there is result on surfaces on multi-dimensional. Although it's using completely different techniques, this gave us hope that maybe if there is manifold without boundary, because like here of circle, maybe you can prove this S-limit shadowing. But there is small problem, which also say that you cannot be that much optimistic that in every case you can prove, if you have shadowing generic, you can prove this S-limit shadowing, and this is kind of result who says that in many cases it's impossible. So that's also quite recent result. Okay, so what he proved, so this is Kawaguchi, he recently has some papers about shadowing, a few recently published. Okay, so what he's setting, so this is differentiable manifold. Okay, and he was interested in looking at shadowing on sign recurrent classes, so he like proved this result first, but then in next paper, or maybe in next paper he realized some connection. Okay, so I will try to like sketch you what he proved, or what are the consequences of what he was proving, because that will be an explanation by picture why in some cases you cannot have this S-limit shadowing. Okay, so what was his argument? Okay, so I have this manifold. And then what he said, okay, I had this result, so from that, by some other results, what I can conclude is that if I look at set of all chain recurrent points, then that's Cantor set. Okay, so here I have Cantor set somewhere in my manifold. I have Cantor set of chain recurrent points, so all others are not chain recurrent. All right. And then he says, okay, because it's Cantor set, so here I pick somewhere some open set, I take point. Okay, and this point is not chain recurrent, but definitely its orbit, if I iterate it forward or backward, it has omega limit set or alpha limit set, and that's subset of chain recurrent set. Okay, so these go somewhere, start to approximate. Backwards also start to approximate this chain recurrent set. All right. But then he says, okay, so what I can do, if I approach here some chain recurrent class, arbitrarily sufficiently close, I can jump into it and finish there. Okay, so he says, okay, if here is somewhere chain recurrent class, if I go very close, I will jump inside and then I will stay there. And also backward, if I'm close, chain recurrent class, I jump here and I will stay there. Continuing, but like normal orbit. But like looking forward. Okay, so now assume that I have this S-limit shadowing property. So what I will produce, I will start very close to here and I will finish in some chain recurrent class, provided I was able with X go close to it. Alright. But then he says, okay, but there is kind of hierarchy in chain recurrent classes, and they are called initial and terminal chain recurrent classes. So there is always kind of structure that if I have chain recurrent classes, then initial means that it's the top one. So from that one I can go with chains to maybe others, but there is no other class from which I can start and go with chain to it. That's initial. Okay? So maybe structure is like that. These are pseudo orbits, and this is terminal. Okay, so there is hierarchy of classes like that. And this is okay, but by one of the results in this chain recurrent set, these initial classes are dense. Initial classes are dense in chain recurrent sets. So now see what he's doing. Okay, I start X, I go here. I'm very close as I wish to chain recurrent set. But initial chain recurrent classes are dense. So I jump into that one and I finish there. Alright? But this point is coming from somewhere. So he says, okay, I'm using this asymptotic tracing, so I have points starting somewhere and finishing in my chain recurrent class. So I have two possibilities. If I was starting somewhere else than this class, then that's contradiction because it's not initial. Because I have another class, I can jump out and finish here, and I should see picture like this. But maybe it is the same one. But then this point was chain recurrent because I can start here, jump, but it's not. Okay? And now it's the essence of that proof. He used lots of results, but that's the essence of the proof. Right. So like, if you want to have something like that, first of all, you cannot have situation like this. That is, you have this Cantor set and complement. And in a sense, it was like here because I was showing you this. Okay, let me go back. Okay, in that class, what was nice, that in typical map, the dynamics was global, so everything was chain recurrent set, and that was like kind of prerequisite for this. Right, so still maybe there is hope, like to prove it in that setting. That I'm not sure. But anyway, definitely it won't be, I mean, so good candidates, again, like summing up, so good candidates for proving genericity is the cases when you have this S-limit shadowing at least dense. For that space, we don't even know that, but it seems possible to prove it. And it really would be nice to have this genericity of this property except like one dimension, but we don't know. We were also trying to prove it for interval, but for interval we failed, and the reason was that there are endpoints. So endpoints really make life hard. So it's why we have it on circle, but not on interval. Okay, and maybe I will stop here. That's enough. Thank you.
Thank you very much. Are there any questions? Will be online. Can you maybe return to the slide about method in dimensions? You know, I just wanted to ask if it makes sense here to talk also about mean dimension, or because everything here is method. Because you know the difference is that topological entropy is actually invariant, even though we can write it with in the language of the metric, whereas the metric mean dimension is not an invariant.
Well, so what I can say that I can say one thing, that what we even couldn't prove, and it was kind of hard thing, so we were trying like maybe to show that maybe these two are, or maybe when these two are the same. But with that we have even problems. So at least for what we were doing, this was very important to use this in the definition. Okay. So this was like, in all estimates, this was crucial. That's looking at separated set. So I don't know how to like even attack it without it, if it answers your question. But also like would like to see here equality of these mean dimensions, but it seems it's not true actually. But we don't have formal proof, but it would be really nice to have them equal, and there are some cases where they are equal, but here we couldn't prove that, at least under these assumptions.
I still have another question.
I have a question, but it's regarding a comment that was on one of the slides. So you had a comment that this S limit, whatever S stands for, S limit shadowing and the normal shadowing is typically filled by different points, and I wanted to ask about that. You didn't say
No,
that's the third. Yeah, that's the third dot. So because that's very very strange. Could you say something about that?
Right. So the comment is that, okay, so here I require these two things. So first I have shadowing, and here I have, so this is stronger version, but if I forget about this pseudo-orbit, so if I have asymptotic sequence, then tracing, I can do asymptotic tracing in that sense. And what this comment is that there are systems when you have shadowing, so you can, any delta pseudo-orbit you can trace. When you have this asymptotic one, you can trace, but in a sense you cannot combine these two properties together. So you don't have this one.
So it has to be a different point?
Yes, so there are some asymptotic pseudo-orbits that you can trace asymptotically, but not with epsilon related to delta.
Okay, but is it somehow, okay, the word typical doesn't work here, but is it like there's a very, very specific orbit when this happens, or is it like kind of typical? I'm not going to make a topology of the orbits. I don't want, I have no idea what this means, but I'm asking if your example, because I assume it's your example, it's like, do you build a very, very specific pseudo-orbit when this breaks, or is it like, do we have a set of pseudo-orbits, or is it like typical in some sense?
So the reason, more or less, I will maybe try to sketch it if I remember it well.
I'm not sure if I'm asking the question properly.
The very sketchy picture is that, okay, so I have this sequence or the space, and somehow maybe I can move here with this decreasing accuracy, and maybe make some loops. But what happens is that if I have this delta for epsilon, then in some sense this tracing will be living here. If I decrease epsilon, this tracing point will have to live in some space, but will never move beyond some boundary in a sense. So imagine like if this was sequence accumulating here, and maybe here was fixed point, then for asymptotic tracing I can take this point, whatever was that orbit, because from some point on I will be arbitrarily close here. But if I have also some path, and this path is pseudo-orbit, and if I want to trace it, I cannot simply go here. This is the kind of thing that happened. That if I allow myself to to go very close, and I'm in some sense unable to trace. Because I make some jumps, or I like define this pseudo-orbit in such a way that if I want to trace it, I have to stay in some region. But I'm making smaller and smaller and smaller, and that's more or less the reason for this, very roughly speaking. But so there is some point tracing pseudo-orbit, which is living here, but for epsilon I don't have to go very close here, but if I want to make it asymptotic, I should move very much to the right, and I cannot do that. That's, in a sense, the reason, without like giving concrete example.
Okay, so I think we can thank Piotr again. Those who would like to join us for lunch are welcome. And then we will go after the lunch, we will meet at the theorem, right?